So, using aldehydes and ketones, this is our last chapter, and we are going to discover our new homologous series in this portion. And that homologous series or that functional group alone can be converted into two main parts, one of which is known as aldehydes and the other one ketones. So, this chapter is going to cover both of them. So, aromatic carbonyl compounds. Carbonyl compounds is our functional group. And when I say the word carbonyl, I actually tend to mean carbon doubly bonded to oxygen, and that has capability to make two more bonds. That is carbonyl compounds. When I use the word aromatic, that means there is a benzene group attached to this whole portion, and that can be either to the right of it or to the left of it, whatever it is. On the other side, definitely there is more part of the chain. Now, that has very distinctive element-like odors. Benzaldehyde is used to make almond essence, the flavoring used in some cakes and puddings. Benzaldehyde is also a component of mixtures that make up the smells of and flavors of many fruits. It includes mangoes, cherries, apricots, the list goes on. So, benzaldehyde and the structures of heptane 2-on is also shown over here. So, let's take a look at it. Okay, where are they, by the way? Benzaldehyde, yeah, there they are. So this is heptane 2-on, and this one is benzaldehyde. Now, as the name suggests, benzaldehyde, the name comes from benzene, this entire six-membered carbon ring, and then there is aldehyde. Aldehyde represents this exact specific part. Now notice this is the carbonyl group we were just talking about, the carbon double bond oxygen, which technically means that aldehydes have an hydrogen atom attached to one side of it, which actually breaks the whole chain. If there is only one hydrogen atom, so you cannot extend the chain on this side. On the other side, however, you can expand the chain for which we already have a six-membered big carbon ring. So that's why the name benzaldehyde. Looking at the other counterpart, that is the carbon group right over here. And on this case, you would see a carbon chain going all the way to its right and all the way to its left. So you see five carbon atoms on its right, one on its left, including this carbon, which is carbonyl carbon itself. We actually have a total of seven carbon atoms, hence the name hept. Since they're all singly bonded, hence N. And since this is a ketone, this was an aldehyde. And by now, you know aldehyde is this carbon is carbon. On one side, we have hydrogen. On the other side, we can have any kind of chain. Now, this one is going to be a ketone. That's why this ONA and this suffix, the matching suffix. And you clearly have the idea carbon and carbon is in between two carbon chains, and both carbon chains are on both sides, which can again be same or different. In heptane 2-on, obviously the carbon chain length on both sides is different. So that's what is the concept of aldehyde and ketone. Although the same concept with both sides carbon chain or one side carbon chain and one side hydrogen for ketone and aldehyde respectively have been cleared in the very first chapter of organic chemistry. I'm talking about chapter number 14. I'm talking about the portion of 14.2 where we cleared out all homologous series, including their functional groups, the names, one of their exemplar structures, and their names as well. Now, this clarifies this part for us. So let's move on. More complex aldehydes and ketones also occur in common smells and flavors. The lemon odor of citronella candles. The citronella candles can be used to repel mosquitoes. Now, citronella candles are very common in the areas where there are a lot of mosquitoes. Now, I would rather quote some tropical areas over here, any countries that actually lie near or on the equator or on the poles are have too harsh of environments, both kinds of environments. The ones that are near to equator are too hot. The ones that are near to poles are too cold to have mosquitoes. Rather, the ones in between tend to have some natural environment, which is pretty favorable for mosquitoes. So mosquitoes is one of the biggest problems over there. So let me tell you, when I say mosquitoes as the biggest problem, actually, if we calculate human death due to the reason of any other living being apart from microorganisms on the planet, no, I think most humans haven't died because of snakes or because of alligators or because of sharks. Those are just movie cliches. Actually, most of the humans have been died from mosquito bites, malaria, dengue, and then there are many other names which actually top the list. So that's why this is an important example when it comes to that. The aldehyde is actually responsible for the smell in citronellal, and you can see the aldehyde group has already been bold over here, which again gives you the idea that this uh, carbonyl carbon along with this hydrogen and this whole R, this is commonly in a single line writing is written like this. So this CHO actually represents the aldehyde group, which is taken out from lemongrass, for which the tea is pretty famous, the citronella grass, for which we have the candles, which are very famous. And you can also see another functional group in this whole chain. So this gives you the idea of it. Okay. So moving on, uh, showing you different chemical compounds, talking about their composition gives the student an idea or an edge of getting familiar with different new compounds. Now, when you're going to go through the past papers of A levels, you will see that organic chemistry is filled with those examples. You would see 2 to 3 examples in every season in every year's paper. That's why coming up with different examples for different structures, quoting their names, their function groups, showing their structures is a very good way of the book getting you familiar with those things. So that the paper doesn't come as a scary thing for you. The more you're familiar with different kinds of structures, maybe longer chains, maybe rings, maybe some mixture of both, it would actually make chemistry a little bit easier for you, even through its presentation. So coming on to 18.1, the homologous series of aldehydes and ketones. Not to forget that aldehydes can be formed from the oxidation of primary alcohols. And I would also like to quote over here the alkenes. You may quote the specifics if you want to, and I'll be very straightforward that the alkenes that had H and R were actually converted or oxidized into this. Now, if I simply, for the sake of the word oxidation, add an oxygen over here, take a look. This is actually the structure of aldehyde. I just simply added O, and of course, the oxidation reaction is going to add oxygen to a structure. And there you go. This alkene space structure is already converted into an aldehyde. I couldn't make this point back in the alkene chapter because you weren't familiar with the structure that much. But here, I can easily do that. Now, I'm going to do the same thing with the next line, and the next line is about ketones, and that's the oxidation of secondary alcohols. Now, I hope in secondary alcohols you do understand that the carbon that is connected to the alcohol group, which was this group, is supposed to be connected to 2 other carbon chains or carbon groups. That can be big chains, that can be a single carbon chain based alkyl group, it can be anything. Now, the same goes for alkenes in the similar sort. If I quote it for the alkenes of the similar sort, I hope you do understand that I have to erase this part and I have to convert it into a double bond. Now, as soon as I add an O because of the oxidation reaction over here, there you go. That's the structure of a ketone. So it's pretty easy to understand as well as to remember how the alkenes or the alcohols, whether primary or secondary, are so easily converted upon oxidation to their carbonyl counterparts, aldehydes, and ketones, respectively. I think it is as much easier to see as much easier it is to put on the paper. I don't know whether you're going to agree with me or not, but this makes a lot of sense to me. Okay, so let's move on. In aldehydes, the carbon atom or the carbonyl group is bonded to carbon atom and a hydrogen atom. And then on the other side, there is a carbon chain. In ketone, the carbonyl group is attached to other carbon atoms or chains. So this is the difference that I've already cleared. I think this was just the repetition of it. Moving on, a little bit of examples for the structures, also for the nomenclature. So as you can see, the carbonyl carbon is the part of the functional group. We are supposed to calculate it as a part of the chain. So if you have just that carbonyl carbon, of course, that's going to be methanol. Now, the point I'm trying to make over here by breaking down this name into different parts is that this is going to be methanol because one carbon is meth and it's singly bonded to its chain sides. The single bondedness is only checked for these parts, not for oxygen. All right. So that is N, and Al stands for aldehyde, which obviously gives us the idea if this chain consists of a double bond, like we had an example, and I'd like to go back just a page or two to quote my example. Now, this kind of example, now remember, in this case, whatever the total number of carbon atoms is going to count as a part of the parent chain, the name would not end in like meth, N, and then L. Of course, the suffix is going to be there, but it won't be N. It will be in because of the double bond. So this gives us the idea whether how the chain or the broken parts of the name act. So I hope you understand how and why we put this "an" before the suffix "al" in these cases. Now, if this much is clear, I hope you understand the next members of the homologous series already. That is ethanol and propanol, butanol, pentanol. Now, I hope you do understand that this CHO in these cases is not just the suffix at the end of the name. In fact, it's just one end of the structure. I hope you understand in aldehyde, it's actually problem, what you can say for the structure itself or the functional group, how it works, this carbon has to be the terminal carbon. We can also use the stylish word, this carbon has to be the corner carbon, one side of the chain. So take a look in this numbering, this is number one, in this numbering, this is one, this is two, in this numbering, this is one, two, three, in this numbering, this is one, two, three, four. But since it's every time one, we're not supposed to put it over here. So you won't see butane 1L. That you won't see. Since alcohol can be placed anywhere in the chain, you can either put it over here or you can put it over here in the chain. So that's why it was divided in two parts. For this part, it was butane 1-ol, and I'm matching it with alcohol to make sure you understand how the name changes. And it would be butane 2-ol for the other isomer given below. So this gives us the idea that in case of aldehyde, CHO is usually, and if that's the only functional group, it would be usually the terminal carbon. Terminal means a corner carbon, the carbon which gets to have the start of the side of the structure, and possibly if that's the preferred functional group, it would also be the start of the counting of numbers. Of course, that carbon would get number one in the counting. Moving on, second table is for ketones. Now, since ketone has chain on both sides, this clearly gives us the idea that this carbon would be usually in the middle. This carbon cannot be the terminal carbon whatsoever in ketones. So ketones start with the very basic of having three carbon atoms and hence drop. So if this is supposed to be in the center and there it should be at least one carbon chain over here and one carbon chain over here, so of course it's going to start with the member which has at least three carbons. So ethanone and methanone do not exist because they can't. The way this whole formula works, they can't. They don't even ask those questions anymore. It's not uh, 2002 or 2003 paper that so they're going to ask this kind of question, but the questions existed before. Now, obviously, Cambridge do understand that the student also already had the perfected the perception of or the idea that how this formula or this entire functional group or the homologous series works, so they don't ask this question anymore. I hope you understand. In IGCSE, there was a question about alkenes, that why methane do not exist. Now, the simple answer was that carbon-carbon double bond needs at least two carbon atoms. And the name talks about having just one carbon in the structure. So this won't be even possible for methane. That's why methane does not exist. And alkenes start with the structure of ethene as the first member. In a similar way, ketone starts with propanone as the first member. Then there is butanone. Since the carbonyl group can be placed at any point in the chain, so pentane can have pentane 2 on or 3 on, but it can't be 1 on. This gives us the idea that 1 is never going to be the number for this suffix on. If it is, it's definitely wrong, which means in paper 1, if they try to confuse you with 1 on, that structure is obviously wrong. Don't fall for the trap. Don't try to imagine the whole structural formula and waste yourself the time. I am putting time to it so that you don't waste your time in paper 1 for 1 on and falling for those names. I hope you get my point. And this also clarifies how do we name them. So Al is the suffix for aldehydes and on is the suffix for ketones. So moving on. Before we move on, would it be okay if you can go through their skeletal structures yourself?
Yeah, sure.
Because there are no skeletal structures over here, but I hope that you would be able to draw the skeletal structure for this one yourself, like this.
Yes.
Right? So if you understand my point, for propanone, either for butanone or pentane 2-on or 3-on, I hope you would be able to draw the skeletal structure. Same goes for aldehydes. In aldehyde, we are supposed to show the group CHO at a point like this instead of this doubly bonded O. So I'm not going to go with more detailed examples. I hope you will be able to do it yourself. If not, you can ask me that as a question at any time. Right? So moving on, the second point that we usually go with in the organic chemistry chapter, apart from alkanes or alkenes, since we dig them out of the core or we take them as a part of our reserves of fossil fuels, for alcohols, for aldehydes, for ketones, for esters, for carboxylic acids, we tend to go with the preparation portion. That tends to be the very next portion right after nomenclature and name or structure understanding. So starting with preparing aldehyde. Genetic equation for aldehyde is made from a primary alcohol. So primary alcohol and oxygen atom from an oxidizing agent gives you aldehyde and water. So we have done with this equation. So you already know any one O would give you um, uh, an aldehyde, the same counterpart aldehyde actually, if there won't be any carbon chain differences, increase or decrease in this equation. It simply adds or converts the oxygen in the oxidizing agent portion. Or you can simply say that it also takes the hydrogen out of it. So since it takes hydrogen out of it to make water, it gives you the idea how come it's oxidation. So the oxidizing agent used is a solution of potassium dichromate 6, acidified, a little bit warm, better with dilute sulfuric acid. To make the aldehyde, the primary alcohol is heated gently with the said oxidizing agent. The mixture turns green as the orange dichromate ions are reduced to chromate 3 ions. These color changing along with their ions have been discussed before, so I'm not going to put time on them. But how we convert this alcohol and aldehyde and stop it from being converted to its carboxylic acid, because if I let this reaction proceed even a little bit with the oxidizing agent, it would be converted into a carboxylic acid. Propanoic acid, the name would be. So, how to stop the reaction at aldehyde and not let it convert into a propanoic acid is something we're about to cover in this practical activity. So, let's clear it out how we're going to do that. So, the acidified oxidizing agent is added one drop at a time to warm primary alcohol. The aldehyde made is distilled off as it forms in the reaction vessel. This method works because the aldehyde product will always have a lower boiling point than the alcohol reactant. So as you can see, we have this whole thing in the form of a reflux already. So ethanol plus the acidified potassium dichromate 6. So it says like that, but as said in the wording, you can use it with the help of a thistle funnel added drop by drop at a time. Okay. So we need to reflux and move the aldehyde into another portion. We can't let it stay inside the reaction mixture, and that's what stops it from being converted into the counterpart carboxylic acid. So the reason is also mentioned over here. Since the aldehyde would have a lower boiling point than the alcohol reactant, so it's easier to actually reflux it and move it to the other side. If the aldehyde is not distilled as soon as it is formed, upon a little bit of further heating, the acidified dichromate solution will oxidize the aldehyde into a carboxylic acid and the product would be changed. So it gives us the idea how we can produce ethanol from using ethanol. So this is ethanol and this is ethanol being converted with the help of an oxidizing agent. Of course, if you don't reflux it to the other utensil at the same time, it could be converted into ethanoic acid. Okay, the aqueous ethanol form smells like rotting apples. This is an idea which is given over here, which is not written on top of it. Well, this has been used in past MCQ past papers, so that's why I wanted to point this one out. Moving on, preparing ketones. Now, secondary alcohols in the similar way of oxidation with an oxidizing agent can be converted into ketone and water. Again, we have taken out hydrogen atoms in order to proceed with this oxidation. So this activity is pretty simple and straightforward. So you don't see a big paragraph for it or a big diagram. Why? Because even if we do not go for reflux, we can convert it into ketone. Why? Because the ketone is not converted into any other product, and the same thing is mentioned over here. So we take the oxidizing agent, we take the secondary alcohol, we put them in the reaction mixture. The color will change from orange to green once it is converted. Unlike aldehydes, ketones cannot be further oxidized. So even if you heat the mixture under reflux and add excess of oxidizing agent, we do not need to distill off the ketone product immediately. And that's why we do not need to distill it off. Okay. Now, here is some very important points that you need to understand. So if in the exam the question says oxidizing agent and use an alcohol with it, and they tend to mention that this alcohol is converted into a inorganic product, so it can be aldehyde. I'm trying to mention their words, how they go with a clever way. Sometimes, and they put warm over here. Now, sometimes what they do is that they put excess over here. They still keep the word warm or they replace it with sometimes with heat. Of course, it won't stay in the form of aldehyde because the reaction proceeds to form carboxylic acid, right? So they give you the idea. Now, they can also play with some prerequisites that we had back in IGCSE or we have here in the book. They say that they don't have the excess, they simply heat it, and the smell comes out to be the alcohol is ethanol to be specific, and the smell is for rotting apples. Now they are clearly trying to point out they're forming ethanol because that is similar to rotting apples. Now they don't put the excess over here, they heat it up and then they say that the smell is a little bit vinegary. That means it's not aldehyde, it's a carboxylic acid. That means it stayed inside for such a longer time that it was converted into a carboxylic acid. Now, the smell is not specifically pointed in this book over here, in this chapter or the previous chapter. So it gives you the idea that they may be playing with the information given in this book or the information that comes in the previous IGCSE book, which comes as a prerequisite to you. So they can play with any of those hints to come up for you to come up with the right product, right? And sometimes they don't even quote the reflux over here. And then if you don't quote the reflux, the alcohol can be the secondary alcohol and the product can be the ketone because they know they do not need to distill it off immediately. Now, these kinds of hints give the student the idea that where, in which direction is the question going into. Okay, moving on, if we go forward on the reduction chain, we can always move backward. On the oxidation chain, we can always move backward towards the reduction side of the chain. Remember, I told you that the alkenes can be converted into alcohols, the alcohols into aldehydes, and then into carboxylic acids or ketones, but this can always be worked backward. So if the aldehyde plus reducing agent, what's going to happen? The exact opposite would be converted into a primary alcohol. That for a ketone would be converted into a secondary alcohol. Now, the reducing agent is used usually as an aqueous alkaline solution of NaBH4. Now, this is the first time that they are quoting that they use it as an aqueous alkaline solution of it. All right, which actually, in comparison, gives us the idea that this LiAlH4 is a stronger reducing agent, and we can't use water along with it, so that's why it's used in dry ether. Or this is somewhat a weaker reducing agent, which can be used with aqueous alkaline solutions. Now, the aqueous alkaline solution clearly states it has water in it, but that water is not going to affect its working. So in both the cases, yeah, we can carry out these reduction reactions, but they have certainly different conditions. I hope you understand the fact. Moving on, reduction reaction is carried out either by warming the aldehyde or the ketone with this, or you can add this dissolved in dry ether, such as diethyl ether. At room temperature, the organic solvent has to be dry because LiAlH4 is a more powerful reducing agent, the same words, than NaBH4 and reacts vigorously in water. This gives us the idea of why the difference in condition. And this piece of information has been manipulated in past papers towards answers. Now, since we have been using this O symbol in oxidation equations, we can use this A symbol in reduction equations. We did the same in the previous chapter, chapter number 17. So you can see the ethanol being converted into ethanol and propanone being converted into propan-2-ol, the secondary alcohol. So hopefully it clarifies the idea. Now, you have been seeing the opposite of these equations. So if they do make a mind map and if they convert it for you, I hope you are able to clear out the mind map by answering questions. Let me clarify by giving a quick example. Now, if they write something like this, now, now if they write something like this over here and here, what these conditions are, or what this organic product is, I hope you can clarify them. Now you already should know the conditions to these reactions, or you can how you can go back and forth on the oxidation or the reduction chain. So clearly this one is reduction. And since we have clarified either one of the reducing agents can be used under different conditions, Clearly, this one is oxidation. We have clarified the oxidation conditions earlier, and clearly this one is aldehyde because the alcohol is primary alcohol. So these kind of mind maps, and this is actually a small one and a really easier one. What they're going to do is that they are going to make big mind maps, which are going to cover half or the entire examination page to give it a scary look and to scare the students away with just one paper and one page. And that happens a lot in organic chemistry papers. As soon as you're done with topicals and you move to yearly papers, you are going to go with that kinds of questions, and those will give you the idea that why most of the chemistry students tend to call organic chemistry a more difficult part of it. Moving on, nucleophilic addition with HCN. This clearly gives us the idea. Now, remember, nucleophilic addition was the addition that was based on some components that may have the negative charge, this one, maybe this one, all right? Or if they don't have a negative charge, they have a lone pair because of which they act as a nucleophile. Now, the word addition clearly tells us that this is going to be an addition reaction. We would probably be resulting in a single product, and that single product would have both the reactants added to it. So now we do understand what the words like addition or elimination or substitution reaction mean in organic chemistry, since we have been doing them from past 3, 4 chapters. Also, we do understand the words how the nucleophilic or the electrophilic reactions are carried out. Now, the electrophilic addition reactions were carried out along the carbon-carbon double bond, and that specifically happened in alkene molecules. But for aldehydes and ketones, like the topic says, we're going to talk about some addition reactions with the help of HCN. Now, in HCN, you do understand that H is the positive, but CN is the negative part of it. And this definitely is a nucleophile. And that nucleophile is then going to carry out some addition reactions across the CO bond. Since we have the carbonyl group present over here, that nucleophile is going to attack it, and that is going to go for an addition reaction. Now, in this nucleophilic addition reaction, what happens is that the aldehyde propanol is heated with HCN. The HCN is generated in situ, which means HCN may be the reactant, but HCN is not the reagent. Now, in order to mention the reagent, he has mentioned the reagents over here on the equation. Potassium cyanide, also written over here, and dilute sulfuric acid, also written over here. This dilute sulfuric acid and KCN are going to react. KCN plus H2SO4 are going to produce for us HCN plus KHSO4. This is the actual equation that goes with, and this HCN is produced in situ, which means right there and then in the reaction vessel to be reacted with our aldehyde and converted it into a addition product. Now, this addition product seems a bit difficult along with its structure and naming, but this is really easy if we go with the mechanism, which comes right after this page. So let's keep moving on. Let's go towards the mechanism so we can make this entire structure and addition easier. And let me tell you, this might seem a little bit scary over here, but if you go with the systematics, this is going to be the most um, uh, one of the best parts, which are very easier to understand. Okay. So note that the carbon atom has been added to the propane molecule by the addition of the nitrile group. Also, this is a useful reaction for chemists because that makes for them new compounds, increases the carbon chain length by one carbon atom. Remember, in the case of nitrile, that actually is a very, very important point. And you are going to use this important point to your advantage in organic chemistry papers. In the past paper, whenever you see that they start off with, let's say, a two carbon based structure, but after a couple of reactions, they convert it into a three carbon based counterpart. That means in between these reactions, they might have used the nitrile. But how would they convert a nitrile into another organic compound? This is what you are about to see. So the nitrile group, which then attached, can easily be hydrolyzed to a carboxylic acid in this kind of reaction. This is an acidic hydrolysis, and it would remove the nitrogen out of the structure in the form of NH4Cl. Now you can hydrolyze nitrile group by refluxing it with the dilute alkali, such as NaOH. If that happens, what's going to form is that you are going to form a sodium salt of carboxylic acid with it. So if I be exact with that, let's write it up. There can be separate water, but we don't write water because water also comes as a part of the product. Yes, that's how it goes. No, this equation doesn't. That's not it. Well, I'm going to clarify and confirm this equation to you. I might be making a mistake over here, but let's move ahead. So the mechanism of the nucleophilic addition, the one I was talking about previously. Okay, so the carbonyl group in aldehydes and ketones is polarized. Now, I hope you clearly understand. In between carbon and oxygen is more electronegative, and this is going to be partially negative, partially positive. Whatever the chain over here, this just this part of the structure gives us the idea that Cn negative, being an nucleophile, would be able to attack it. And that's exactly what happens in step one. So the Cn negative is able to attack it. Take a look, it's negatively charged or it has a lone pair. Well, both of them are shown to give a clearer idea because this tends to keep one electron from HCN. That's why I was saying that the HCN itself is broken down into two parts, H positive and Cn negative. Since this Cn is negative because it tends to keep the electron from hydrogen, that's why this lone pair, which can attack this, then one of the bonds move over here. This arrow does not mean the entire double bonds move on oxygen atom. No, just one of the bonds out of these two bonds move to the oxygen atom as a negative, and that's what happens. CN is attached to the carbonyl carbon, not any other carbon of the entire chain, just the carbonyl carbon, and those parts of the chain are still intact. It may be a ketone or it may be an aldehyde. Okay, so the oxygen stays over here with negatively charged, and this stays over here positively charged. What happens is that this negatively charged oxygen in the second step can attack another molecule. It can attack the positive part of the molecule, the hydrogen, and the bond is kept by CN, and it generates a negative ion for the next reaction. Hence, it keeps on working as a loop, and we keep on forming our product. This is our product. It's always going to be 2-hydroxy, and then there is nitrile on the same carbon atom. This is nitrile, this is hydroxy. Now, you might be asking that why we are putting hydroxy. If a compound consists of OH, we usually use the suffix ol. Now, let me tell you a rule of nomenclature. If a compound tends to have two functional groups, one is this one, then we give preference to one of the functional groups, and whichever one gets the preference will have the name as the suffix. The other one would automatically be converted into a prefix. So it's not ol anymore for alcohol. This means this got second preference, this got the first one. Why the first one? Because it consists of carbon atom. Of course, this carbon atom would be one, this carbon atom would be two, hence 2-hydroxy, not alcohol or ol anymore, 2-hydroxy, and the one is the position for nitrile. We don't need to mention one, we can simply go for 2-hydroxynitrile But if there is a longer chain, you may mention it. But even if you don't, when you mention 2 hydroxy and a simply nitrile without the one, it automatically actually represents to the reader that nitrile got the preference. Since it got the preference, it must have the numbering of 1 during the counting of carbon atoms. So, moving on, all aldehydes and ketones form 2 hydroxynitriles when they undergo nucleophilic addition. This is because hydroxyl group will always be on the adjacent carbon to the nitrile group. Uh, this is shown over here. Nitrile group is the first carbon atom, the adjacent one. The second carbon atom or the carbon atom connected right next to it is known as the adjacent one. So this adjacent has OH group on it. Now, starting with the aldehyde methanol, the hydroxyneutrile formed in this nucleophilic addition with HCN would be hydroxyethane nitrile. Why ethane? Because now we have extended the chain. Now, understand the point that he's trying to mention this for you. Now, if this CN is going to attack this carbon because it is partially positive and this one is negative, this would go over here. This would be converted into HCO negative CNH, right? So if we move on, this is going to attack the positively charged hydrogen for CN, and this would definitely be converted into a structure like this, OH. Now, this is hydroxy ethane nitrile. Hydroxy means it has alcohol group. Eth means it has 2 carbon atoms. We do not need to number them. Ane means they are singly bonded. Nitrile means this gets to be the preferred functional group, hence the name like this. But for bigger chains, we can definitely put numbering to this. Now, in this case, there is no need to insert 2 because the same reason I just told you. But in the upcoming ones, we can obviously put numbers. Okay, so testing for aldehydes and ketones.